Hello everybody. In this video, I am going to show you how we can bypass some of the Frida detection techniques that are being used in Android application these days. These in-app protection techniques such as Frida detection, root detection, hook detection, and there are other few techniques as well that are used by the applications in order to protect themselves from an attacker. Now, just to be clear that this video is intended only for educational purposes to allow us to apply these techniques during pen testing and to responsibly report any findings to the product managers in an ethical manner. So for this video, we are going to use MSTG crackme application called R2Pay, and the link to download this application is in the description box down below. So here you can see in my R2Pay crackme directory, I have already downloaded this application, and here we have our rooted Android device. So let's quickly install this application from the terminal. All right, using adb install R2Pay, and the installation is done. So now you can see that the application is shown here, right? So let's launch the application in order to see its behavior. So if I launch it, we can see that it got crashed immediately after the launch without showing any UI or any error messages. Now there can be multiple reasons for this, but just to make sure that there is nothing wrong with the application build, you can try running this application on a non-rooted device, and if it works, then most likely the application is detecting something like whether the device is rooted or not. So for pen testing, most of the time we use rooted Android devices, so we can assume that the application is detecting root over here. But for this video, I am not going to cover how to bypass root detection in this application, as I have already created a separate video where I have explained how we can bypass root detection. So you can go and check that out. But as a bonus, let me show you a quick and easy way of bypassing root detection without using Frida, which should work for majority of the applications. So for that, we need to have Magics Manager app installed on our rooted device. So here you see this settings application down below. This is my Magics Manager application, which I have disguised it as settings application. Okay, and I would suggest that you also disguise your Magics Manager application because sometimes the application do detect suspicious applications like this. So now in this application, if we go to the settings and down below, we can see here we have this digest module which is enabled, and then we have this configure denial list. So if we go inside this, we can see all the packages or all the applications that are already installed on the device. Now all we need to do is just enable this check on this R2Pay application, and that's it. Root detection should be bypassed now for this application. And if our assumption is right that the application is crashing only because of root detection, because obviously the Frida is not running as of now and we are not hooking anything, so it has to be root detection. So if I launch it now, the app is working perfectly fine. Okay, so just to give you some context about what's going on behind the scenes of this digest module, it basically unmounts all the SU related paths from this application, and the app thinks that it's running on a non-rooted device. Okay, next let's try to explore this application by looking into the decompiled code of this APK. So for that, split my terminal, and using JADX GUI, I am going to view the decompiled code of this. Let's minimize this for now. Under documents, tools, I have my JADX GUI present, and under the bin we have the executable of JADX GUI. Alright, so if we open the file R2Pay, so here in the left pane you can see the packages that are being present in this APK, including the resources and everything. So this is the source code, and if we go into the resources, we have this Android manifest file over here. So this we can say is kind of an entry point for any application. Whenever the application is launched, based on the main activity or this intent filter, the activity will be launched first. So from this first attribute that we are currently looking for is the package name. So here on the top we have the package name, and that is re.pawnme. So what I'm going to do now, let's go back to our terminal and let's try to spawn this application using Frida. But yeah, of course, first of all, we need to turn on the Frida server on our device, right? So by going to the shell using adb, going into the root mode, and then I have the Frida server present in this data local temp directory. So now the Frida server is running on our Android device, and now let's launch it using Frida -u for USB, because our Android device is connected through USB cable. And let's launch the application forcefully. So for that we have this -f attribute, and then the package name that we have just seen, that is re.pawnme, right? Hit enter, and the application is launched, but it got crashed after that. And here Frida also shows us the crash log. So here we can see that the error that we got is segmentation fault, that is 6seg, and the fault address is this. The value of the program counter is this, and in the backtrace, so in the backtrace we can see that the crash occurred in this libnative library, right at this offset. So this actually gave us a starting point, like, okay, where we should look for next. Now we are going to look into this library because that's where the crash is originating from. Now in order to do so, we first need to extract our APK, and for that we are going to use APK tool. So our APK is already there in this directory, as you can see. So using APK tool, decompile r2pay APK, hit enter, and now it's going to take some time in order to extract all the asset classes and all other resources. So the unpacking is done, and if we see, we got a new directory here with the name r2pay, and if we go inside this directory and see its contents, we can see all the files, assets, and libraries that are packed in this APK file. All the native libraries are present in this lib directory. So if we go into this lib, we have all these different architectures. Our device is currently running on ARM64, so that's why let's look into the 64 version of the native library. And here we have actually two libraries present. One is libnative and another one is libtoolchecker. So as of now, since our crash was originated from libnative, so let's only look into this one. For disassembly purpose, we are going to use radare2 as our disassembler. So let's disassemble this libnative.so file using r2 and then the library name, hit enter. Okay, so now this native library is being loaded by radare, and using AAA, we can tell radare to start analyzing this. So now the analysis is started and it's going to disassemble and try to figure out all the functions, strings, and everything from this library. Now this can take a couple of minutes depending on the length of the library. Okay, so the analysis is done now. Now first of all, let's start the analysis by looking at the functions which are discovered by radare. So using AFL command, we can get all the functions, and here we can see that the function names are stripped out, and these names are given by radare based on their offsets. Then here we do have some imported symbols which are coming from external dependencies, and then we can see some decoding functions. So based on the name of these functions, we can assume that these are responsible for doing some sort of encoding or decoding of data. So these functions are not giving us any hint what's going on in this library. So next, what we can look for are the imported functions. So all the imported functions we can see using II command in R2. So these are so in this imported functions, let's try to find out some of the interesting functions that could be responsible for Frida detection. To give you a basic idea about Frida detection, most of the time the application look for the Frida artifacts. So whenever the Frida server runs and whenever we spawn the application using Frida, Frida leaves some traces in the memory and in the file system, and based on those artifacts, the app detects whether Frida is running or not. Let's try to find out here what are all the functions that are responsible for any kind of file system manipulation, right? So here we have open function, which is used to open any file into the memory. Then we have lstat, right? So let's do one thing. Let's try to hook on these open lstat functions first and see what's being called by the application, right? So let's open our Visual Studio, and over here, let's create a script file. Now in Frida, we have interceptor.attach method that allows us to intercept and modify the behavior of any function. It also allows us to specify a JavaScript function that will be called every time the target function is called, and we can use this function to modify the argument passed to the target function along with its return value and the overall behavior of the function. So for that, let's create a JavaScript function hook open. So for each of the interesting imported functions, we are going to create these JavaScript functions, and then using interceptor dot attach API of Frida, we are going to perform the hook. So this interceptor dot attach API of Frida takes two arguments. First argument is the address of the function where we want to hook, and the second argument is the target function. So first of all, let's try to figure out the address where our open function is located. Now, since all these imported functions are not defined inside this libnative, but these are coming from some other dependency or other external libraries, right? So for that, we are going to use module.find export by name. Now this find export by name function takes two arguments. First one is the name of the library where our open function is located, and then the second argument is the name of the function itself. Now in Android, we already know that all these imported symbols are coming from libc, so we can define libc.so as the first argument. But if you don't know about any of the imported function from where it is coming from, you can leave the first argument as null. Okay. Then the second argument is going to be open, that is name of the function. And now this will return us the address where this open function is located at in the memory. Then the second argument is going to be the target function, which we can define like this, and it has two attributes, on enter and on leave. So on enter has one argument, that is args, and this on enter will get triggered whenever this open function is about to execute, right? And in this args we will get the arguments that are being passed to this open function. Okay, since we are interested in printing out the arguments to this open function, that's why we are not going to define on leave. And over here we can console the argument like this, open. So this args is basically a pointer to array. So in order to access the first argument of this open function, we can access it by indexing it starting from 0. And then the argument type of this open function is string. So using read c string, we can read the argument as a string. All right. Okay, now let's call this function and launch the application using this script. And let's see what are all the files that are being accessed using this open function, right? Okay. So here we have our script.js, right? Using Frida -u. Then we have this -l attribute, which we can use to specify our script. So using -l script.js, and then the package name, that is re.ponme. Hit enter, and this will spawn our application using this script, and we should be able to see all the open function calls in this console. Right, again we got the crash as expected. But if we scroll up a little bit, we can see that our open function is being triggered multiple times. And here we have the argument. So first of all, it opened base.apk, then some files, and then we can see that it has accessed data/local su. So some root detection related files it has accessed. But since we have already bypassed this check using Magix Manager, we don't need to do anything about these function calls. Alright, so in this particular trace, we can see just before the crash, there are no traces of Frida. So then let's move ahead and see in the imported function what the next function that we can hook, and that is lstat. So let's try to see that. Going back to our script, and let's try to create a similar function, hook lstat. Again using interceptor.attach module.find export by name. The library in which this exported function is present is libc.so. Then the name of the function that we are going to hook is lstat, and then let's define the target function, and inside on enter we are going to print out the arguments again using console.log to print out the arguments. Lstat, and the first argument of lstat is the path name. So using args0, we can access the first argument and reading it as a string using readc string, right? Nothing new, just like what we did for open, same we have done for lstat, right? Okay, so just like the previous one, let's call this hook lstat function as well. And coming back to our terminal, let's launch the script again and see in the console what all the traces we got. So again, the crash at the same offset, nothing new. And if we scroll up, we can see that there are traces to the open function just like the previous output, but there are still no traces of lstat. Okay, so just before the crash, again there is nothing new in the output, so we can say that the lstat is not doing anything as of now. So moving on to the next interesting function, that is going to be snprintf. Okay, so this snprintf function, let's try to see what are the parameters that this snprintf function takes. So if we go to the browser, in the browser we can search for snprintf definition, and here at the top we can see that the snprintf function is defined is used to store the specified string till a specified length in a specified format. All right. So if we look at the arguments, of this snprintf function, it has a character pointer string, which is the buffer, and then the size, and then the format. Okay, so whatever the string that is being specified here, this snprintf function will convert it based on this format and store it into this buffer. Okay, so what we are interested in is this pointer string buffer. So in our script, let's create the function to hook snprintf. Let's copy paste this, and instead of lstat we are going to hook snprintf. And since this snprintf is going to store the string by formatting it into the desired output in the first argument, that's why we need to look at that particular argument only after the snprintf done all its processing. So for that reason, this time we are going to print the output or the argument in the onLeave method, and it has one attribute called return value. So this return value will contain the value that is being returned by this snprintf, but we are not interested in that. We are interested in this args0 argument of this snprintf, but this argument 0 is only available inside on enter. So we need a way to somehow get this argument in the on leave. So for that, over here, let's create a variable argument 0, assign it to null initially. Then here argument 0, we can assign it to the actual one. Okay, this is not needed here anymore, and this now we are going to use here using this arg0 variable instead of this one. And here also, instead of this, let's print snprintf. All right, so now whenever the snprintf function is being executed by our application, this target function will be called, and when this function is triggered, we will get the reference to this argument pointer in our local variable. And then at the time of exit from this function, this only will be triggered, and at that time we are going to see this output. All right, let's call this here. Now going back to the terminal, let's launch the script again using Frida-u and spawn the application. And now in the output, we can see again the crash at the same offset. And if we scroll up, then we have snprintf. Okay, so now we have something new. And in this snprintf, we can see that it has access /proc/self task, then some ID, and then the status. So here we can observe that this snprintf function inside this libnative library is iterating over this proc self task directory and looking for the status file. And these are basically the thread IDs. So what this proc self task in Android contains, basically this proc self task directory is a virtual file system in Android that provides information about the task or the threads that are running in the current process. So each subdirectory, that are these directories, these are the threads or the thread ID that are currently being running in the current process. Okay, so we can assume that using this snprintf function, this libnative library is iterating over all these threads one by one and looking for a particular thread which contains something suspicious. So in this case, whenever an application is being launched using Frida, there is a separate thread with the name of gmain launched in the application process, which is used to inject code into the main loop of the running program. Okay, so most likely that's what this library is detecting using this snprintf function. And just to manually see how these status files looks like during runtime, let's do one thing. Let's again launch the script using Frida and spawn the application. But this time let's tell Frida to launch the application in pause state using -pause. So now application will be launched, but in the pause state. So now we have to explicitly tell Frida using this %resume command to start executing. So here in the device, you can see that the application is launched in the pause state, and that's why we are seeing this white screen. So now if we go to our ADB shell, let me launch another terminal. Here, let's go to the ADB shell. Let's make use of the root permission, and then first we need to identify the process ID of the running application using ps-a, and then grep only re.pawnme. So this is the process ID of the running application. Here, instead of self, we need to put actual process ID, because this self is a symbolic link which points to the actual process ID in the application at runtime, and then the task. And now if we list down all the directories using ls, we can see that these are all the threads that are currently running in the application. Now let's see what's inside this first thread. Here we can see that there is a lot of information available related to the running thread, like process mapping file, file descriptor info and everything. But the application is opening status file, so let's see that one. Using cat command we can print out the content of this status file. So over here we have some information about the process, and then at the top we can see the thread name, which is re.ponme. So this first thread is actually the thread of the main application. So that Frida detection logic inside the libnative library is basically iterating over these threads individually. One thing to note here is that whenever we launch the application, these thread IDs will be different every time. So we can't simply rely on these thread IDs statically. But let's try to do one thing. Let's see how many times this snprintf gets called here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So here in our output we can see that this snprintf gets called only 14 times. But if we go back to our ADB shell terminal, here we can see that these threads are definitely more than 14. So 14, 15, 16, 17, yeah, so in total 17 threads are there. So based on that we can assume that in this 14th thread it has detected something. So let's manually see first what's inside the status file of this thread. So by printing out the content of this file using cat command, first we need to go inside that particular thread subdirectory and then print it. Now let's check the name. So the name of this thread is gmain, right? So this gmain thread is something which gets launched when we hook or spawn the application using Frida, and this is the thread which is responsible for injecting our JavaScript code into the running process. So based on this gmain thread, the application is detecting the presence of Frida. Now what I would suggest you guys to do is you go inside the proc self task directory of any other process which is not spawned by Frida, and see all the subdirectories of the threads and check whether this gmain thread is there or not. So in order to bypass this, we can create a fake status file and point the first argument of this snprintf function to point to a fake status file instead of pointing to the original one, which does not contain any thread with the name gmain, right? Let's do that. So first of all, the easiest way to create the fake status file is to make use of the original one. So what I'm going to do, since this 12405 is the one having the gmain, so let's go to some other thread, let's say this one, and let's print out the contents of this status file into a fake status file, and that I'm going to store inside my data local temp directory, fake status. Okay, let's come out of this terminal as we don't need it anymore. And now inside this, over here, let's create the logic for providing the fake status file. So first of all, we need to make sure that we are going to replace only when snprintf function is storing our proc self task status file, right? So for that, using arg0 read the string dot index of, and if it contains slash status, okay, then only modify it. And now in Frida, we have this write utf8 string method. Using this, we can simply pass the string which we want to write. And just now we have stored our fake status file into slash data slash local slash temp, and then the fake status file. So that's what I'm going to pass over here, fake status. Now what's going to happen is at this address that is being pointed out by this arg0 variable, which currently contains this proc self status string, that is going to be replaced by slash data slash local slash temp fake status. So now instead of looking into the status file, the logic or the algorithm is going to look into this fake status file, which actually does not contain any reference to the gmain Frida artifact. So this should probably do the trick, and we should be able to bypass this check, right? We know that this lstat is not actually contributing us anything, so let's comment it out. So let's save the script, and over here, okay, so currently the application is in the pause state, so let's kill it and launch the application again. And if everything is fine, our check should be bypassed. Again, the application got crashed, but now the offset is different, right? And in the trace we can see that we have something new in the snprintf trace. So our snprintf is now pointing to the fake status file, and we can see that this time this snprintf function got triggered more than the last time. After that, it started looking for proc self fd directory, right? So first check related to Frida, which is looking for the gmain artifact inside this proc self task directory, is bypassed, and now something else is being detected, and most likely the check that is being triggered is because of this file descriptor. Okay, so based on this trace, we can say that again this snprintf function is responsible for detecting Frida based on the artifact that is being present in this fd directory. So in Android, this proc self fd directory basically contains all the file descriptors which are being opened so far by the application. Okay, and let's scroll down a bit. We can see that the last file descriptor that this snprintf function checked is this 46. Okay, so let's observe one thing. Whenever this crash occurs, let's see what is the last file descriptor that is being accessed. Okay, so this time we got 46. Let's again launch the script without any changes and see what is the file descriptor this time. So the offset is same, and the last file descriptor accessed by snprintf is 46 again. Okay, so just like the previous one, this time let's see what's inside this 46 file descriptor of proc self fd. So again, launching a new terminal, but before that we need to launch the application in the pause state, right? And then in our terminal, going to the shell of the device, taking root permission, and then looking for the process ID of this running application, that is 142.47. So going to the proc process ID file descriptor ls. In total, these many file descriptors are currently open by the application. We need to go into the 46th file descriptor. Now note here that these are not the directories anymore. These are the symbolic links which are pointing to the actual file, right? So if we want to see where these file descriptors are being pointing to, we can use ls-all command. And now the 46th file descriptor is being pointing to Frida server injector, right? So this is another Frida artifact which the application look for in order to decide whether the Frida server is running or not. In order to bypass this, again, we can use the previous logic over here. Instead of this 46th file descriptor, we can point the snprintf to any other file descriptors, and that would work, right? Because in all the previous file descriptors there is no Frida artifact. So let's do that again. If this time we are looking for proc self fd and whatever after this, that is not our concern. Let's point it to slash proc self fd, let's say 45, just before the 46th, and this should do the trick. So going back to our terminal and launching the script again. I forgot, let's resume it. Okay, great. So now we have the application running. You can see everything is running. Okay, and in the output now we didn't get any crash, and in the snprintf trace also you can see now all the fds are being pointing to this 45 only. If you observe one more thing, just give it some time. So you see again these file descriptors are being triggered. So this is a thread which is being executing in the background continuously by the application to detect the Frida server. Okay, right, you can see that we are able to generate the R2 coin as well. Okay, so just to summarize all the things in this video, we have seen that this R2Pay application is having Frida detection, and basically it is detecting for two Frida artifacts. First one is inside the proc self tasks status, where the Frida gmain thread is present, and by iterating over the task directory of the device, if it encounters the gmain thread, it will trigger check and the application will crash. Then after that, similarly, it is checking for another artifact that is present in the proc self fd, and if the file descriptor contains the link to Frida server, then it will also trigger the detection and the application will crash, right? We have managed to bypass these checks by pointing the snprintf function to the fake ones, right? So that's all I wanted to cover in this video, and there are other ways also to detect Frida. I will try to cover some other detections related to Frida as well in the upcoming videos, so stay tuned for that. And if you haven't subscribed to the channel, then please go and subscribe first. and also hit the like button.